I'm Jeff Denworth, VP of Products for Vast Data, and thank you all for joining. So we're just going to get right into it and explain the Vast story. Okay, so Vast was an idea that started in the very early days of 2016 when the company was founded. Started by a gentleman, Brendan Halak, who previously was the head of R&D for the Extreme IO team. I'll get into the concept in just a moment, but just to give some perspective on the timeline and our relative maturity, we did start shipping systems at the end of 2017. These were proof of concept systems, prototypes to some early adopter testers and customers. We were fortunate enough to work with dozens of organizations, some of the best and brightest minds in the industry. And they certainly ran the concept through its paces. We did announce our version 1 of our product to our customer community, at least in November of 2018. This was a milestone event for the company. At that point, we started shipping to production customers. And that brings us all the way to today. So 3 months later, you've seen that we've now announced the company. We decided to take a slightly different approach than a lot of the other companies that enter into the market. We weren't lacking customer demand. We had more than what we could deal with. And so we figured we would hold back the launch of the story a little bit into the public sphere, such that we could make sure that there was enough customer validation behind the announcement, and we'll talk about that in a moment. We're also today announcing our funding. So the company is capitalized with around $80 million of venture capital. And the cool thing is that in 90 short days, what we've established ourselves as the fastest growing early stage IT company in history. We're selling, in many cases, in our first 90 days, more than some of the leading companies in the flash and hyperconverged backup space sold in their first year. So we're getting orders in the range of dozens of petabytes combined, and we are fortunate to have customers that have put the system through the paces so much that they're confident with writing checks in the $1 million plus range. So an extraordinary outcome, at least in the first 3 months of operation for the company, that's really a byproduct of what we think is a very cool product concept, coupled with the fact that the system really is working well and going through the paces as customers expose it to a rigorous battery of load tests, failure tests, things like this. I should also point out that we are hiring. So the company is today around 80 people in size. We probably need to double the company this year alone. So if you're good, if you know anybody else that's good, this appears to be a rocket ship and we need good help. So feel free to tell everybody that Vast is hiring. Okay, that said, let's start with the origin story of the company and how this all started. When the company was founded, we had the fortune to work with a bunch of early customers, collaborators. We had hundreds of customer discussions. And in the early days, we were often asking customers what else they needed from all flash storage, which is a seemingly simple question to ask. And what we were most surprised to find when we were asking this question to customers is that none of the customers came back to us and said they needed any more performance than what they could get from the generation of flash systems that you could buy around the mid-2010s. And so when we stopped having a conversation about performance, we started having a broader conversation with these customers about how they manage their data. And the conversations quickly focused on a compromise or a trade-off that customers have been facing around how they architect their storage environments at large, one between a trade-off between performance and capacity. And this basic principle of storage tiering that Gartner introduced 30 years ago is something that every customer is dealing with today. We can talk with customers that have anywhere between 5 to 10, even 20 different types of storage systems in their environments. And There's a variety of reasons why customers like flash. They like it because it doesn't break as much, it doesn't hotspot. But the reality is that the limitations exposed by today's systems that customers can buy in the market have forced them to create this complex pyramid of infrastructure that's both difficult to manage and also expresses some application challenges. And then we went and looked at what's going on in the cloud, and we said, okay, what's different there? And what we realized is if you go to any modern cloud provider, typically they're offering these classes of storage services just as a service. And really there's no new innovation there in terms of different types of storage concepts that are being introduced. So when we started to look at the problem, we saw it as twofold. One is that the data center stack is today overly complicated. Customers are dealing with a big collection of technologies. They're moving their data all around the data center all day long for application reasons or because they're trying to save money by moving data down into slow archive systems. But the bigger challenge is that as we think about the modern applications that are starting to emerge into the data center, and specifically I'm talking about big data and machine learning and deep learning, what we found is that unlike the applications of yesterday, what you have now is a new class of codes that customers are trying to deploy that don't expect to act and interface with data as legacy codes have. And in fact, a lot of these new deep learning and machine learning tools, they get more efficient and they get more accurate as you expose them to more data. And so in essence, these new codes are expecting a storage experience that's completely contrary to how that pyramid has been built for the past 30 years. And so what we realized is that the pyramid is dead, but the problem was that there's still the issue of what the technologies are underneath them. And as we started to think about why that trade-off between performance and capacity exists, as best as we could tell, it all came back to the hard disk, a piece of media that gets bigger every year, but doesn't get any faster. And of course, you have longevity issues as you start to field these devices into the market for more than a few years. And so this creates an opportunity for customers to save money based upon capacity, but from a performance perspective, everybody knows that the hard drive is not the best solution. And our first big aha moment was when we started to think about the fundamental nature of flash. This is a device that breaks the fundamental trade-off that has existed between performance and capacity for the past 30 years. A flash drive of 10 years ago had 1/10 the performance, but also 1/10 the capacity that you can get today. And so everything scales linearly with flash. You get performance with capacity, or you get capacity with performance. And you could think about the idea of an all-flash data center where if you double the size of your data, you instantaneously double your ability to compute on that data, which is the nirvana that everybody wants to get to. Of course, the big challenge is the cost of infrastructure. Today, if you were going to compare at two ends of the spectrum, a high capacity hard disk, 7,200 RPM, let's say 14 terabytes or so, that'll cost you around 3 cents per raw gigabyte. On the flip side, if you wanted to buy a enterprise grade SSD, dual port NVMe SSDs can cost you as much as 60 cents a gigabyte. And this 20x gap has resulted in an experience where customers can't justify spending 20 times more on infrastructure than what they have in the past. And as a result, they continue to create this complex hierarchy of infrastructure. They continue to tier their data either within systems or across systems. And this is ultimately the gap that VAST realized that could be our mission to narrow. What we wanted to do was to rethink how storage could be built, and as a result, come out with a new outcome that created the opportunity for new behaviors in terms of how customers build data centers and how customers deploy applications on storage. We call this concept universal storage. And what we did is we spent the last 3 years engineering a lot of different ways to bring the cost of infrastructure to a point that would be no more expensive than your archive. This is a system that delivers tier 5 cost efficiency, but it's built entirely from flash. There is no hard disks in the system. There are no tiers in the system. It is 100% NVMe store. where we write at 3D crosspoint speeds and we read at NVMe speeds. It's a clustered architecture that allows you to scale to exabytes, and in aggregate, the performance can give you terabytes a second of performance or millions of IOPS. And so the first trade-off that VAST has sought to break is the one that has always existed between performance and capacity. Now we have a system that gives you the performance that you would expect from a tier 1 storage system at the cost of a tier 5 storage system. As I mentioned, it's very scalable. The next trade-off that we wanted to break was run around protocols. So we built a distributed NFS and S3 storage system, large enough such that it can encourage customers to consolidate all of their data and all of their applications onto a single tier of flash. But the interesting thing is that we realized that once you can deliver a system that delivers both NFS and S3 performance at NVMe speeds, you don't make the same decisions around protocols as you have in the past. Up until now, people tend to think about storage as you use block for speed, you use file for ease of use, and you use object for either scale or for cost. And in our case, we've erased the considerations that go around these protocols. Our file and our object storage interface perform at the speeds of an all-flash block device, and they cost equivalent to what people today pay for object store. So that's another trade-off that we've broken. The ultimate objective is to represent a new and different type of data center, one that is built entirely from one tier of storage, something that's fast enough for your fastest applications, it's affordable enough for your deepest capacity requirements, and it's resilient enough such that you can trust all of your data with it. And so this is our vision. This is the universal storage vision. And the nice thing that comes out of this, if you get there, is now you've elevated all of your data up to NVMe media and made it available at NVMe over fabric speeds. And the point is that the ability to derive insights, the ability to mine data, the ability to run new AI algorithms, the ability to just get to any piece of information or any answer in real time now becomes ultimately possible. And so there's a lot that goes into how we put it together. People typically are very suspicious of us when we make these claims. And the first thing to understand is that we were fortunate to start with a few technologies that weren't available before 2018. And the engineering effort at VAST basically was focused on building a new type of architecture from the ground up, not to retrofit these technologies into an architecture, but rather to rethink how storage could be built and made using these new technologies to the best of our advantage. And so when we started the company in 2016, we had to make forward bets on these technologies. In fact, none of them were commercially really rolling at that point. And if they didn't all come in, then we wouldn't be having this conversation today, but we're fortunate that they did. The three technologies are as follows. NVMe over Fabrics. NVMe over Fabrics is a new, very low latency storage protocol that can be layered on top of commodity networks, Ethernet at data center scale, InfiniBand at data center scale. NVMe over Fabrics has only 5 microseconds overhead to get to an SSD on the other side of the network. And if you look at any CPU that's accessing that SSD, it looks as if it's directly attached, even though nothing is directly attached. And so NVMe over Fabrics allows us to disaggregate this, our system architecture, and decouple the CPUs from the physical media. We keep media in pools of highly available enclosures, and the CPUs are built into stateless containers that you can spray across your data center. This global view that comes from NVMe over Fabrics allows us to execute a lot of new types of codes that weren't possible before this very, very low latency, very scalable fabric. But the challenge with NVMe over Fabrics is that it works best with NVMe media, and NVMe flash is the most expensive flash that you can typically buy today. And so when we looked at the opportunity, we realized that just over the horizon was a new type of flash. QLC flash, both in terms of its read performance, is a spectacular piece of media, reads at just the same performance as an enterprise MLC or TLC drive could. On the flip side, there are a variety of reasons that customers don't, or excuse me, other storage companies can't use these devices, even though they are so much lower cost than traditional flashes. And the principal reason is that these devices can't be overwritten nearly as much as storage devices could in the past. MLC or TLC media has something in the order of 10,000 more write cycles than QLC flash. And so these drives need to be written to in new ways, and they need to be written to in a very, very specific manner that requires at least a fair amount of buffering of I/O as they go into these drives, such that I/Os can be crafted into a perfect form. And that's where the third technology that we made a bet on comes in, which is Intel's new 3D crosspoint memory, also known as storage class memory. Crosspoint you can think of as cheap, persistent RAM. It has the persistence of flash, it has speed that's just a little bit less than DRAM, and it has a cost that's dramatically less than DRAM. And so with storage class memory, what we can do is we can build big distributed pools of NVMe attached memory that sit on top of QLC flash. We buffer writes as it goes into the system, and we shape writes into perfect QLC erase blocks as it's going down into the QLC flash, such that we don't encourage any what's called write amplification. I'll get to that in a moment. So storage class memory is the way to enable the use of the lowest cost flash. For us, it's also a place where we keep all of our metadata. We're enriching the system with way more metadata than you would typically find in a modern scale-out storage architecture. And this metadata allows us to drive up the efficiency of the system and consequently drive down the cost. So here's what the system architecture looks like. It consists of two different types of systems. At the bottom here, what you have are HA enclosures. Today, these can be as large as 600 terabytes of QLC flash and a little bit of storage class memory, around 15 terabytes or so. In the back end of these enclosures are two active servers. The servers don't run any of our logic, though. It's not a shared nothing architecture. The servers just provide active access to all of the devices, and you could think of each of these enclosures as a big dumb JBOF, just a bunch of flash enclosure. Now, because they don't have any logic in them, they don't have to communicate with each other. They all just scale out on an NVMe fabric, and you can build as many as of 1,000 of them into a cluster. And so from a raw perspective, that's something in the order of 600 petabytes of raw infrastructure that you can build in a single cluster. After our data reduction, that could be anywhere between 1 exabyte to many exabytes in size. Now, the logic all runs in this process up here in our servers and our containers. So you can think of the computing power of the system being 1 part protocol server and 1 part global flash translation layer server, all rolled into a Docker container. These are entirely stateless machines, so there's no storage in them whatsoever. We're not persisting any writes to them. There's no metadata that needs to be stored in these systems. They all enjoy direct, low latency access to all of the flash devices that sit on an NVMe fabric, as if they were all direct attached to each of the servers or containers. And so on the left-hand side, you see that we can build dedicated file object servers that sit on your network. These can expose NFS and S3 namespaces out to remote clients, all within less than a millisecond. And you could have 10,000 of these servers within a single cluster. You can size performance for whatever performance that you need by just adding more servers. And if you need more capacity, you just grow the cluster by adding more enclosures. There's no absolute fixed ratio of servers to enclosures that you need. We have archive customers that just want a few servers and a lot of enclosures. We have other customers that say, I need absolute lowest latency of access. Give me a lot of servers and just a few enclosures. But this containerization of our software and the fact that we build everything in stateless systems means that we can start to think about deploying infrastructure in ways that haven't been done in the past. And in this case, what we realize is that we can actually embed our containers into the customer's compute environment. We can publish a VAST container as part of a compute node or a client or a host. And that container then becomes a little local loopback device for the applications that are running on that same system. This has the benefit of bringing the performance of NVMe over fabrics all the way up to the host. Now we can expose our internal parallel protocol to every one of your application servers such that they get the full performance of NVMe over fabrics, but at the same time, the application experience just enjoys the simplicity of NAS. So this disaggregated shared everything architecture, we call it a DASE architecture, we believe is far superior to shared nothing cluster designs. And the first reason for that is that when you can build a system that has stateless servers in it that don't need to communicate with each other, building infrastructure, from the perspective of a storage company is much simpler. The cool thing about this is that the architecture is completely parallel. Every single server accesses all of our consistent data structures that live in the enclosures in real time, and they are always seeing a completely consistent view of the namespace. In addition to that, there's no crosstalk, so none of the servers have to talk to each other in the synchronous write or read path. And as a result, scalability becomes much better because you don't have to worry about how things slow down as you have more and more systems that communicate with each other in a cluster. On top of that, there's no cache in the system whatsoever. So that also means that there's no cache coherency code that needs to be implemented across the servers, which is one of the most challenging things for storage architects to deal with is how do you build a system that appropriately manages data from DRAM down to some sort of persistent media in the case of a failure or power outage. We don't have any of that. The system can crash at any line of code and we bring it back up in a fully consistent state. That also means there's no batteries. That also means when a server fails, there's no rebuild that has to happen over the network. We can have all but one server fail in a cluster and you continue to remain online. Obviously performance is lower, but that's a nice thing to have if you lost, let's say, a dozen servers. You can still keep the system up and running. And then finally, because we build in Docker, we have the ability to auto scale the infrastructure up and down based upon the requirements of the applications. And if for some reason the applications start to get really hot on the cluster, we can build tools to integrate with things like Kubernetes where it spawns a few new servers, the application gets better performance, and maybe when the load gets lower, those servers get given back to the data center. These are all things that are possible because of this disaggregation and the statelessness. But the other nice thing about the shared everything architecture is it lays the foundation for a bunch of new global algorithms that we've invented. That can build a global namespace using consistent metadata structures. It does global flash translation for QLC, global data protection with only 2% overhead, and global data reduction that can find opportunities for efficiency where it's never been possible before. You can start with as little as one enclosure because there's no single point of failure in any enclosure, and you can scale to however many you need. As I mentioned, if you need performance, you scale out servers. If you need capacity, you scale out enclosures. Now, one of the cool things about this design point that we have with this disaggregation is that now we have the ability to pool these servers in ways that is suitable for people that want to build private cloud infrastructure. What we realize is that we have a lot of customers that say to us, yeah, it's great that you guys can consolidate all of this stuff, but my users still expect that they're going to get their own systems. And in our case, what we can do is we can pool and dedicate ingress and egress points to specific applications or specific tenants because we make a multi-tenant storage architecture. And that allows you to kind of brute force quality of service to those users. And at the same time, our multi-tenancy model comes in as an additional layer of data isolation where we can limit the exposition of certain tenant data to servers or to VLANs that run specific pools of servers. And so now you get better security isolation as well as better performance quality of service than what has been possible in the past. Okay, so there's three ways that customers can deploy this. We have most regularly today, we're shipping systems that have servers attached to some amount of enclosures. We also have the ability to deploy our containers within a customer environment, and they just have to deploy our enclosures. And then for very large customers, they can deploy our software as a software-only solution on top of some qualified hardware. Okay, so the appliances have roughly 580 terabytes of raw QLC flash. Each of them has 400 gigabit Ethernet or InfiniBand ports coming out the back, and that's 2U. After our data reduction, if you were to get to say 4:1 data reduction, that's roughly 1 petabyte per rack unit. The servers, we package 4 servers in a 2U chassis that has 8 50 gigabit Ethernet ports inside of it, and those all get connected up to the NVMe fabric. As I mentioned, you can scale each of these linearly. So as you need more performance, you add servers. As you need more capacity, you can just add some additional capacity and things start to scale. There are no set limits on what configuration you have to buy. Okay, so the question is, if these servers are all stateless, first, how do you build the namespace? How do they understand what's in these enclosures? And the way that we do this is that we implement a new type of data structure that we believe is designed for exabyte scale. And in the system, what you have is each of the servers runs, or containers runs a little consistent hash table within it. This hash table, as servers try to do read, write, or metadata functions, will issue a quick hash function. The response from that hash function will indicate to the server what enclosures it needs to talk to in order to complete that I/O operation. Now, as it talks to these servers, it's talking over NVMe over fabrics. This is a very, very low latency fabric. And each of the round trips to the enclosures is a RDMA transport, so very, very low latency. In the enclosures is a new type of tree structure that we use to articulate the namespace. It's an adaptation of a computer science term called a B-tree. We call this a V-tree, and for the reason that it's different from how B-trees have been built up till now, it's designed for extremely wide fan out. Each layer of the tree can be hundreds of times larger than the layer above it. And that means that we only have to build a tree that's 7 layers deep to support a system that can support into the quadrillions of inodes or objects within a cluster. As I mentioned, there's no DRAM cache. Every write to this tree happens from the bottom up, and every write to the system is an indirected write, so you can think of it as a transactional storage system in that regard. These V-trees, they're all distributed across all the enclosures in parallel. They're designed for shared everything access so that all of the servers don't need to talk to each other. They just need to talk to the trees that live within the enclosures. And the data structures are such that everything's self-describing. The lock state is in the metadata. The snapshot state is in the metadata. The directory composition is in the metadata. So there's no dedicated metadata manager or lock manager or snapshot manager that needs to run in the system. All of the servers have access to the global view, and all of them perform some amount of systems management such that when they write down to the data structures, they're writing actually what is intended from a lock, a snapshot, or a directory state. Now, it is a multi-protocol system. As I mentioned, the first 2 protocols that we're supporting are NFS and S3. These work side by side on top of an abstraction layer that we call the element store. We write them side by side such that we don't want to limit the access to a specific type of data to a specific protocol. So you can write via NFS, you can read via S3, or vice versa. And both of them have equal access to the element store such that there is no performance difference between our NFS and our S3 access. In the element store, what you have is the namespace that's built out of 2 different types of elements. You have attributes. These are mostly key values that are used to express POSIX attributes or S3 metadata, links to other pieces of data in the system, the lock state or the snap state of the specific files or objects. And then you have a data store. Unlike traditional storage systems, scale-out storage systems, we don't have a fixed block size. It's byte granular, thin provisioned, and infinitely scalable. If you store a 1 byte file, that consumes 1 byte of flash plus the additional metadata and data protection data. But we don't have a specific block size where if you go underneath that, you burn a lot of capacity. Similarly, if you store a petabyte or a 10 petabyte file, that just gets sharded up into a lot of different pieces and gets stored across the cluster, across all of the resources. And so everything's fast. The system doesn't view a difference between the files or the directory structures. We can essentially shard up directories and put them all across the system, directory metadata as well, so you can do things like fast lookups. The stack, I would argue, is probably one of the most ambitious first version products in the market. It's extremely featureful, a brand new approach to data reduction that we'll talk about, a brand new approach to data protection that we'll talk about. We have snapshots, we have file locking, we have quotas, we have security, we have support for specific types of S3 operations for specific markets. Of course, there is a simple dashboard to manage the system. So we have a GUI, a CLI, and there's also a REST API that we publish using a utility called Swagger. If you don't want to manage the system, you can kind of let us do it. We have a call home facility where we can monitor your clusters in real time and jump in case of any issue. Okay, so the whole goal here is to redefine storage economics. And the way that we do this is by embracing the lowest endurance, lowest cost flash drives that you can buy in the market today. Talking about drives that can cost somewhere in the order of 1/5 to 1/8 what you would pay today for an enterprise flash device. QLC is great because it costs 80% less than enterprise flash. And it reads at exactly the same speeds, and you can keep these devices in service for over 10 years. The challenges with these devices are that you can't overwrite them nearly as frequently as you can a traditional SSD, enterprise SSD. They're also not dual ported, so that needed to be resolved with our system architecture where we handle that with software. There's no cache power protection. In our case, that gets resolved with 3D crosspoint. So we buffer everything to 3D crosspoint, which means that we don't need a fast cache. And write speed is also not as good because the controllers tend to be a little bit lower end, but we have that resolved by first persisting all the data 3D crosspoint. Now the big thing is around endurance. And customers, up until we explain this, they oftentimes will think that the gains that come from the economics that have been reducing in flash typically come from just process improvements at the flash fabs, but it's not the case. And whereas flash erases that performance and capacity trade-off that we had talked about earlier on in the presentation, we do believe a new trade-off has emerged, one that is around price for endurance or the ability to overwrite the devices. And what we're seeing now is that as these new architectures of flash hit the market, what's happening is that as the silicon can't be overwritten nearly as much, the flash manufacturers and the flash systems vendors have been over provisioning the media. They've been adding more and more overhead to these devices to support a higher level of overwrite than what the media itself is capable of withstanding. And so if you, for example, buy a 15 terabyte flash drive today, you can format this one of two ways. You can format it as a 3 terabyte drive that you can overwrite more than 10 times a day, or you can format it as a 15 terabyte drive that you can overwrite less than 1 time a day. These are all the things that flash manufacturers do to add, let's say, the E in front of these different types of architectures, eMLC, eTLC, and soon eQLC. The problem is that as these drives have to be more and more over provisioned with additional silicon, what happens is that the cost benefit gets erased. And so all of this is because of the way that flash gets written to today in a new type of block size or a new type of geometry called an erase block. And what we wanted to do was to build a new type of system architecture that accommodated for the specific way that low endurance flash is written to. And so what we've built is the first QLC erase block aligned global flash translation system. We write this in software, and essentially we layer it over top of commodity industry standard QLC drives in a way that essentially spoofs these drives such that they don't know anything that's happening at the application level. The way that we do that is through a layer of indirection. Every single write is an indirected write that comes into the system. If, for example, a piece of data gets updated, that just gets put to a new part of the system. And so we control the writes at an erase block size absolutely, and these erase blocks can be very large. If a hard drive based system today can be written to in, let's say, 4 kilobyte chunks, erase blocks can be as large as a few gigabytes in size. And so our understanding is that very few systems in the marketplace will have the ability to even use these new QLC devices for reasons that they weren't written, the software wasn't written to accommodate these new types of drive geometries. And so we always writing full QLC erase blocks, we're writing in multi-gigabyte stripes. And that understanding of the geometry that we build into the system allows us to control the writes absolutely. We allow the drive to be written to, and then the drive only knows one other state, which is that that erase block can be completely freed up. And so that comes from handling all of the flash translation and software in our servers. On top of this, we always write in full write stripes. What we didn't want to do was to build a system that if any piece of data would get updated, the additional data protection drives within a system would wake up and have to recalculate the erasure code. That just further creates more wear on the drives that we wanted to avoid. So this is where that indirection comes back. One of the big realizations, though, that we had is that endurance is really amortized across all of your investments when you can move to a system where you can now afford to keep your long-term and your short-term data on one affordable flash infrastructure. And so we handle wear leveling at a global level. And the way that we think about it is, this is a system that can withstand very pathological applications where if you have a database that's being overwritten once a day, that's fine so long as that database is sitting in a system with your backup data or your archive data as well, because we're just managing towards the aggregate of the overwrite behavior within a customer environment. And we have yet to find a customer that's overwriting all of their data every day. And so this universal storage concept is creates a virtuous circle where we use the lowest cost flash to get the cost of infrastructure down, combined with some unique algorithms. And that resulting effect allows us to use very low endurance drives for over 10 years because customers aren't overwriting their whole data sets every day. But one of the big things that we do here is we take advantage of the fact that we have an unfair understanding of what's happening at the application level, and we implement a new type of write placement algorithms that we call predictive placement algorithms. And the way to understand what we do is first to talk a little bit about how flash gets written to. Today, if you have an erase block that's multiple gigabytes in size, essentially that kind of invites the storage systems the opportunity to create write amplification, because flash drives and storage systems up until now have had kind of one objective, which is to park pages in an indiscriminate manner within erase blocks. And what can happen because of this is that temporary data will get intermingled with long-term data within an erase block. And when that temporary data gets deleted, the long-term data needs to be also erased from that erase block in order to go and get back capacity and give that back to the application. And this creates a write amplification event because that long-term data needs to be moved to some other erase block where usually the storage system will do the same bad things over again and just create this problem of wear, where you could have write amplification that's anywhere between 2 times to 100 times in a system over a period of a decade. And so we took advantage of the fact that we have an unfair understanding of what's happening at the application layer. We can see the file names, the file types, the user IDs, the group IDs, and we develop up statistics within the system that watch the overwrite patterns within specific directories. And with this understanding, what we do is we make predictive guesses about where to place data within specific erase blocks. And that placement allows us to bin writes to specific erase blocks that have specific retention periods. We have erase blocks for 1 day, we have erase blocks for 1 week writing, we have erase blocks for 1 month and 1 year. And as we understand what the life expectancy of a collection of pages are, we commingle them within an erase block of a common expected lifespan. And when the temporary data gets deleted, let's say there's a bunch of swap files that are being stored into the system. After 24 hours, we find that the application's gone and deleted all of them for us. And what that gets us to is a place where we have essentially zero write amplification in the system. The erase blocks naturally just free themselves up thanks to the application. We don't have to move still good data around in the cluster anymore. As a result, we can write a 10-year endurance warranty for the lowest endurance media that you can buy today, which is completely counterintuitive. So the first thing that we've done is we've used the lowest cost flash. The second thing that we do is we write a 10-year endurance warranty for that. So that helps us further our arguments from an amortization perspective versus hard disk-based architectures. The next thing that we wanted to do was to basically make it such that the system gave back more effective utilization to our customers. And so we decided to tackle the topic of data protection. And as a sneak preview, our trick is to write unprecedentedly large write stripes that, as far as we know, haven't been attempted to date. And the reason that this hasn't been done yet in the past, there's a few reasons. The first is if you have a shared nothing system, typically these systems have a CPU that is responsible for a subset of disks, or maybe this is a controller-based architecture where you have a CPU that's responsible for maybe a few more disks. But the problem becomes that within a data center environment, CPUs are responsible only for a subset of the system. In a shared everything architecture, however, you can have CPUs that can see and read and write from all of the devices. And as a result, you can start to implement global codes. Now, one of the problems with very large write stripes, if you can write to everything, is that in order to preserve good write performance, you need a cache. And up until the advent of 3D XPoint, that cache had to be built in DRAM. DRAM's very expensive, so oftentimes that can overcome the savings that you would otherwise get on a wide write stripe. But on top of that, it makes systems architectures more complicated because you have to deal with volatility, you have to deal with power management and failures, and these are things that our architecture isn't complicated by for reasons that we don't have any cache in our cluster whatsoever. And so now it's possible to get good write performance. It's possible to have an algorithm that writes to a lot of devices in one shot. The third thing that we needed to tackle was the resilience. And so as best as we can tell, most storage systems in the marketplace today are built off of some derivative of an algorithm called Reed-Solomon. This is a classic error correction code or erasure code that's used in a lot of different types of architectures. And the basic principle of Reed-Solomon is that when you lose a drive within a write stripe, or you lose a piece of data within a write stripe, you have to read from all of the remaining write in order to do a recovery. Now, if you build a system for wide write striping, the failure domain gets larger. And if you have to read for so much longer because of the bad properties of Reed-Solomon, then it becomes a compounding problem, and it's not practical to use these types of erasure codes with very large write stripes. Now, so what we did is we had to invent our own type of math. It's a new math that we've created that essentially allows us to use all of the redundancies within a write stripe as a force multiplier for our rebuild speed. And the striping that we've implemented is completely dynamic. You can scale it from as little as 40 plus floor to as much as 500 plus 10 or beyond. Both the amount of data that you can build in a stripe and the amount of data protection slices that you can add to the stripe can grow independently. And the way that it works is that for every single additional redundancy or additional data protection slice that you add to a write stripe, this becomes a force multiplier for our rebuild speed. So for example, if we were to build a 150 plus 4, we only have to read from 1/4 of those 150 stripes in order to do a recovery. And so A, the overhead of the system goes down to less than 3%. B, you would need to have 4 devices within a write stripe fail concurrently in order to encounter a data loss event, which is statistically very, 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 very improbable. And C, we're rebuilding at a rate that's 3 times faster than, let's say, an 8+2 style RAID architecture. And so, so these codes scale dynamically across our enclosures. If we, for example, would build a a larger cluster that could get up to, let's say, 500 plus 10, at that point, we can withstand 10 failures within a write stripe, which is statistically impossible. We did the MTDL calculations, or the mean time to data loss calculations, the other day. It's something like 82 quadrillion years. And part of the reason for that is that our architecture is fail in place. So the second that something fails, the recovery immediately begins. The overhead goes down to just 2% in that case. And so now we've cracked the trade-off that's always existed between the cost of data protection and the resilience that a customer experiences. Up until now, typically they'd start to turn down the knob on the amount of redundancy, and they'd start to get worried about losing their data. It's more resilient than, let's say, a triplication-based system, and at the same time, much, much, much more affordable. Okay, so the last thing that we wanted to do in order to address the cost of infrastructure, to make it possible to use flash for everything, is to essentially rethink data reduction. And the way to explain what we do, we first have to explain how things are typically done today. Today you have two methods of data reduction. You have either compression or deduplication that are most commonly used within data centers. Compression is the best way to find patterns within data because it's byte granular. It goes all the way down to specific bytes that you can create a compression dictionary out of. The problem with compression has always been the locality of the codes. So compression is implemented on a block by block or a file by file basis. And the challenge there is that oftentimes customers will have multiple files or multiple pieces of data that express some commonality. And this is why deduplication was invented. Something like 20 years ago, a bunch of engineers said, hey, we can keep a big hash index in memory, use some 7,200 RPM disks, and create a backup appliance that's used to store a bunch of different copies of backups using only references in the form of pointers made in the hash index. Now, deduplication is great because it's a global process. The challenge is that the way that the systems have been implemented up until now, the amount of granularity you can get to is limited by the fact that every single block that gets hashed creates a piece of metadata, and that has to be stored in memory. And so the block size is typically kilobyte range for reasons that you don't want to be storing more hashes than you're saving in memory. And what we realize is that compression creates metadata when patterns are found. Deduplication creates metadata regardless of the reduction opportunity, which is why it's an impractical approach. But when we took a step back and we looked at this topic, what we realized is that in unstructured data, nobody uses data reduction for all practical purposes. If they do, the data's been compressed by the application already. And as data works its way down into the storage system, oftentimes most scale-out storage systems, they won't implement any data reduction. But as we looked at the data and the essence of the data, what we found is that a lot of applications are generating a lot of similar data. The problem is that the differences between the files or blocks that they're creating are just expressed at too small of a level of granularity for deduplication to tolerate. So that's why most people don't use dedupe for unstructured data environments. And so what we tried to do with our similarity-based global data reduction approach is to combine the best of both of these worlds. It's not compression and it's not deduplication. It's a new type of data reduction that benefits from 3D crosspoint first. The system receives writes into 3D crosspoint, the application gets an acknowledgement, and then we start to go to work. On the flip side, we don't have to write data down into Flash and then reread it off of Flash and then write it down to Flash again. So we've avoided wearing down the Flash through our approach. It is an inline process with a background nature in terms of Flash endurance. So as data comes into this buffer, what we're doing is we're chunking it into large blocks or large chunks, and we're fingerprinting this data. The fingerprints aren't cryptographic hashes like you have with deduplication systems today. It's a new type of hash that we invented essentially to measure the relative distance between two pieces of data. We call it a similarity hash. And the similarity hash allows us to group data within the system according to its, the data's similarity. And as new writes come into the cluster, what we do is we compress all of these new writes against the reference block within any similarity cluster. And so now we have something that has the global nature of deduplication with the granularity that only up until now has been exhibited through compression. Now, one of the problems with compressing all of your data together up until now is that if you, let's say, took all of the files within your laptop and you compress them together, first you wouldn't know what the files are within them because you can't see the metadata. But the second problem is that if you have to go do a read, you have to decompress all of your files in order to read them. So we take advantage of the fact that we have all of this random access persistent memory with 3D Crosspoint, and we articulate the reference block ranges and the delta byte ranges within this Crosspoint dictionary such that we don't have to read an exabyte in order to service a 4 kilobyte read. Reads are all done within less than a millisecond using a new type of algorithm that we call locally decodable. And so now we believe we've cracked the code on unstructured data reduction. For structured data reduction, it's also spectacular. We've been doing some testing with a number of backup products, and we find spectacular results. We'll talk about that in a moment. Well, we'll talk about that right now. So one example is some testing that we're doing with Commault software. Commault has its own data reduction tools already built into it. They have deduplication, they have compression. And so we just ran some simple tests where we just let them do what they're doing and let the system compress and dedupe its data as it went down into our system. And when we ran our data reduction algorithms against the pre-compressed and pre-deduplicated data, we saw an additional 6-to-1 gain. And these all compound as you add up the gains that the software in your environment already finds. Now, if we turn off their compression, then we find even better results. 22-to-1 is the level of data reduction that we saw in virtual machine backup sets, all possible because of similarity-based global data reduction. So the objective is to be the extinction level event for the hard disk. We feel that if you can build a system that's fast enough and affordable enough, customers won't be compelled to buy the same types of systems that they've bought in the past. And when that happens, they realize that they don't need as many tiers of infrastructure as they needed in the past. Over a long enough period of time, it could be competitive with active tape. So we'll see. But that's the objective. As we further refine our algorithms and as the cost of infrastructure comes down, the cost will just get less and less and less. So we don't lack ambition, that's for sure. We have kind of our scope on world domination, as it were, but in the early days, we are looking at a number of different very data-intensive applications as our entry point. And what we're finding is that the product is appropriate for a range of applications, everything from AI to backup, high-performance computing to even being used as cloud infrastructure. We've identified a few horizontal applications to work with in the early days. And then we also have a number of vertical markets that may have their own custom tools that they run. These are markets such as the life sciences space, financial services, animation and content delivery, as well as high-performance computing. We did announce today 3 early customers that were kind enough to go on our press release. The first of which is Ginkgo Bioworks. This is a life sciences organization based in Boston. They are a startup that is valued over $1 billion, working on making custom microorganisms. So a really cool company doing some crazy stuff, and they've built out their whole genomics pipeline on top of VAST. Zebra Medical is using new AI algorithms to modernize the patient care process and essentially doing computer vision on CT scans and things like this. Zebra wanted a system that had the performance of a high-performance parallel file system, but the simplicity of a NAS appliance, and we delivered that for them. They'll be running our RDMA NFS server code so that they get better than NAS performance to their GPU servers, and we can keep their GPUs full. And then General Dynamics went on record saying that they're delivering petabyte systems to their customers already. These are US government customers, and we're very fortunate to have them as a partner as well. So that's the story today. We have launched a website at vastdata.com. It is, we're still working out the kinks, so bear with us. You can follow us on Twitter at vastdata, and you can email us at hello@vastdata if you have more questions.